Hello everyone, this is Professor Mahesh Pardeshi from Parvatibai Genba Mose College of Engineering, Wagholi, Pune. We will discussing the thermodynamic properties of the fluids and today we will discuss about the surface tension. Next property is the surface tension. Now see, surface tension is defined as the tensile force acting on the surface of the liquid in contact with the gas or in the on the surface between the two immiscible liquids such that the contact surface behaves like a membrane under tension. To understand this property of surface tension, just we will discuss with the example. We will consider the example of lake. Okay, in the lake, water is standing water, means water is not moving. Okay, the water is standing water. In that water, there is a membrane between the two liquids. First liquid is the water which is stored in the lake, and the second liquid is nothing but the atmospheric air. Air is also one of the liquid. Okay, air is also one of the fluid, not liquid, fluid. So there are two types of fluids, that is liquids and air. In between that two fluids there is a small membrane. There is small membrane which is considered as a, or which behaves as a tension. That's why the property is called as surface tension. The surface is formed between these two fluids. That's why the property is called as surface tension. First thing is the surface is formed, and second thing is it is applying tension. That's why the property is named as surface. So first of all, we will see the definition of it. The surface tension, again, see here, the surface tension is defined as the tensile force acting on the surface of the liquid in contact with the gas or on the surface between two immiscible liquids such that the contact surface behaves like a membrane. Two immiscible liquids means you can take the example of water and oil. You can take the example of mercury and water. Any example you can take. Okay, two immiscible liquids, or it may be liquid and gas. It may be liquid and gas. Two fluids are there everywhere. Two fluids are there, and the layer or surface which is formed between these two fluids is nothing but that surface. Okay, such that the contact surface behaves like a membrane under tension. Under tension, the membrane is always under tension. Okay, that's why the property is called as surface tension. Okay, the surface tension is created due to the unbalanced cohesive force. Unbalanced cohesive force, very important term is this unbalanced cohesive force. I will discuss with the example or figure. Unbalanced cohesive force acting on the liquid molecules at the fluid surface. Again I will repeat, surface tension is created due to unbalanced cohesive force acting on the liquid molecules at the fluid surface. Let us see the diagram. Okay, here the liquid is placed in a one container. Here this is the container and this is the fluid. Okay, here we are considering two particles. This is particle number 1 which is submerged in the liquid, and this is particle number 2 which is at the surface of the liquid. Okay, see the difference between these two particles. Here in case of this first particle, this particle is surrounded by all the other particles of liquid around it. Means around it all the fluid particles are connected due to the cohesion, due to the cohesion. Okay, suppose consider this liquid is water and this is the molecule of water. This molecule of water is surrounded by all the other molecules of water. Okay, that's why because of cohesion, these molecules are connected because of the cohesion. In that case you can see that the arrows are equal and opposite direction. Means if some cohesive force is acting in this direction, equal and opposite cohesive force is acting in this direction. Similarly, the cohesive force acting in this direction, equal and opposite cohesive force is acting in this direction. Here you can say that the cohesive force is acting in this direction, equal and opposite cohesive force is acting in this direction. Means, what is the meaning of it? In case of this molecule, the cohesive force is balanced. The cohesive force is balanced because every cohesive force is balanced by the other direction cohesive force, opposite direction cohesive force. That's why this molecule is in equilibrium. The cohesive force is balanced in this molecule. Okay, now see this molecule, see this molecule. This molecule is at the surface, and in case of this molecule only the cohesive force in this direction is balanced by the cohesive force in this direction. But what about this whole directional cohesive forces? These cohesive forces are not balanced because there is air in the opposite direction of that cohesive forces. Here the cohesion is between the similar particles, that is liquid or water molecules. Here this molecule is surrounded by the other water molecules, and there is cohesion between these other molecules and this considered molecule. That's why there is a cohesive force in this part. This part is subjected to cohesive force. But what about this part? At this part there is no water molecules, there are no water molecules. Here the air molecules are present. That's why there is no cohesion between the considered particle and these air molecule particles. Okay, that's why in case of this molecule, the molecule is under unbalanced cohesive force. What is this? Unbalanced cohesive force. This molecule is under unbalanced cohesive force. Okay, understand the meaning between balanced cohesive force and unbalanced cohesive force. Go through these diagrams, you will understand properly. Okay, now see here, uh, again repeat, I will repeat one line. Surface tension is created due to the unbalanced cohesive force. The surface tension is created due to unbalanced because the cohesive force is not balanced. The molecule is not yet equilibrium. That's why there is some forces which are developed on that molecule, and here tension forces are developed. Okay, the surface tension is created due to the unbalanced cohesive force acting on the liquid molecule at the liquid or fluid surface. Okay, molecules in the interior of the fluid mass are surrounded by the molecules that are attached to each other equally, means the molecule number 1. However, the molecules along the surface are subjected to a net force toward the interior, net cohesive force toward the interior, molecule number 2. Okay, the apparent physical consequence of this unbalanced force along the surface is to create the hypothetical skin or the membrane. The physical consequence of this unbalanced force along the surface is to create a hypothetical skin or a membrane. Means the surface or the membrane is created due to this unbalanced cohesive forces at the surface. Unbalanced cohesive forces at the surface. Okay. See next line. The tensile force may be considered to be acting in the plane of the surface along any line in the surface. Means that force is acting along any line, because at the opposite end there are all air particles. At this opposite end there are all air particles. Means the force is acting in any direction. Okay. The intensity of the molecular attraction per unit length along the line in the surface is called as surface tension. The intensity of molecular attraction, the intensity of molecular attraction per unit length along any line in the surface is called as surface tension. What is meaning of this molecular attraction? Molecular attraction is nothing but this cohesive force. This cohesive force is nothing but the molecular attraction between this considered molecule, that is molecule number 2, with its other water molecules. This is called as molecular attraction. Okay, per unit length. It is measured along the length, and that's why the definition becomes per unit length. Okay, is called as surface tension. Surface tension is denoted by sigma. Surface tension is denoted by sigma, and its SI unit is Newton per meter. Why the unit is Newton per meter? Why the unit is Newton per meter? Because it is a force. It is a force and it is per unit length. It is a force per unit length. That's why the unit becomes Newton per meter. Force per unit length. Force per unit length. That's why the unit becomes Newton per meter. Now we will discuss the next point, sub point, you can say that sub point, surface tension on the liquid droplet and the bubble. Liquid droplet and the bubble. First of all, I have to tell you the basic difference between the droplet and bubble. Basic difference between droplet and bubble. Bubble is formed when there is a air inside that bubble. Okay, bubble is how the bubble is formed. Air is enclosed between some layer or membrane, and that forms the bubble. See, in case of this bubble, the exterior part is subjected to air, atmospheric air, and internal part is also subjected to air somewhat. Okay. So here bubble, the exterior part is also subjected to air, and the internal one is also subjected to air in case of bubble. But now in case of droplet, you can see, in case of the droplet is made up of liquid part. Means all the interior part is filled with the liquid in case of the droplet, and exterior part is subjected to atmospheric air. In case of the droplet, the exterior part is subjected to atmospheric air, and the internal part is subjected to or filled with the liquid. But in case of the bubble, both the interior and exterior part are filled with the or surrounded with the air, atmospheric air. That's why there is a difference between these two difference between the surface tension for these two categories, that is the droplet and the bubble. Okay, consider a small spherical droplet of a radius of a liquid of radius r. On the entire surface of the droplet, the tensile force due to the surface tension will be acting. Now see, we will consider this droplet. Having the radius r. This radius half portion is r, and here the tensile force is acting at along the periphery. Here the force is given. You can see that the force is acting along the periphery. Okay, now let sigma is the surface tension of the liquid. Sigma is the surface tension of the liquid, and dp is the pressure intensity inside the droplet. dp is the pressure intensity inside the droplet. in excess of the outside pressure intensity, in excess of the outside pressure intensity, and r is the radius of droplet. Now next, let the droplet is cut into two halves. Let the droplet is cut into two halves. The force acting on one half, say left half, will be, the force acting on the half portion will be, here you can see that, tensile force due to surface tension acting around the circumference of the cut portion as shown, and this is equal to sigma into circumference. Sigma into circumference. What is meant by circumference? This portion. This portion. Okay, circumference. And circumference is 2 pi r. The circumference is 2 pi r. Therefore, the tensile force is sigma into 2 pi r. Okay. Pressure force on the area pi by 4 d square. Pi by 4 d square is equal to dp into pi r square, means the area, pressure into area, intensity into area. Okay, the pressure force on the area is equal to intensity of pressure into area. Okay, next, these two forces will be equal and opposite under the equilibrium conditions. That is, see, in case of this droplet, in case of the droplet, you have to go through this formula, 2 sigma s upon r. Okay, based on this formula, there may be asking some questions or problems. Okay, you have to by heart these two formulas. Okay, for droplets, the equation is 2 sigma s upon r. 2 sigma s upon r. If the radius is given, if the radius is given, and if the diameter is given, if the diameter is given, this equation become 4 sigma s upon r of a d. 4 sigma s upon d, because r is equal to d by 2. R is equal to d by 2. Therefore, in terms of d, we can write this equation as 4 sigma s upon d. 4 sigma s upon d. In case of bubble, in case of the bubble, the equation is 4 sigma s upon r or 8 sigma s upon d. 8 sigma s upon d. We can use both equations, r or d. If the given data is terms of r, we can use equation of r. If the given data is terms of diameter, we can use the equation of diameter. Okay, these two formulas are important. Okay, learn these formulas. Now, a hollow bubble, like a soap bubble in air, has two surfaces in contact with the air, one inside and other outside. Thus, two surfaces are subjected to surface tension. I will explain this line. See, in case of, bubble, what happens? In case of the bubble, what happens? The bubble is subjected to three bubble is subjected to two types of surface tension. First surface tension is acting inner side, and second surface tension is acting at the outer side. Because both surfaces are subjected to air, that's why this bubble is subjected to surface tension twice. Okay, here in figure you can see this difference. Okay, see this difference. Every point is subjected to double surface tension, one at the inner part and one at the outer part. Okay, that's why the equation also like this. For bubbles, it becomes twice the surface tension. Okay, the total surface tension becomes twice. Okay, here you can see that the surface tension acting is twice sigma s, and here the surface tension acting is 4 sigma s. Okay, now this is all about the surface tension. Thank you for the today's session.